Hello, in this video we're going to talk about Markov chains. So to begin, let's talk about a stochastic matrix. A stochastic matrix is a square matrix whose elements are probabilities and whose columns sum to 1. So let's take a look at an example and a non-example. So here's a matrix A given by 1/2, 1/3, second row 1/2, and 2/3. And we would say this is a stochastic matrix. And let's look at a different matrix B. Suppose B is given by 1/2, 1/2, 1/4, and 3/4. This is not a stochastic matrix because the columns do not sum to 1. Okay, great. So let's take a look. Let's take a look at a theorem. We will not prove this theorem. The theorem says that if A and B are stochastic matrices, then their product is stochastic. So if A and B are stochastic, then A times B is stochastic. And that's going to be very helpful when we look at some applications. So let's take a look at an example. In this example, I'm going to start off with 50 million people. So let's suppose we have 50 million people. So 50 million people living in the cities. And let's suppose that we have 50 million people living in the suburbs. So let's begin letting our initial vector, I'm going to say let x naught be a column vector with 50 and 50. So those are our initial states, and this first entry, this is going to represent our city dwellers, and this second entry is going to represent the people living in the suburbs. Okay, so we have our initial condition, and I'm going to give you what's called a transition matrix. This tells us about the probability that people will move from the city to the suburbs or back and forth. So here's the deal. Let's let P be a matrix of probabilities. So we've got city to city and suburb to suburb. So for example, the probability that someone lives in the city and stays living in the city we'll say is 0.96. City to suburb we'll say is 0.01. Suburb to city is 0.04, and suburb to suburb 0.99. So here's a picture of what I mean. So suppose we've got people living in the city and some other people living in the suburb. Right? And so these are two states. You know, you may not be interested in kind of urban planning, but you might be interested in other systems that have two states or maybe more. And so the idea is there's a probability that you're living in the city and you'll stay living in the city, or more generally that you're in this state and you'll stay in that state after one time step goes by. So this is our 0.96, and we see that right here in our matrix. There are some other probabilities we've got going on. City to suburb, that was a 0.01. That was right here in the matrix. We had a suburb to suburb, that was 0.99, so 99% chance that if you're living in the suburbs, you'll be there next year. And there was a 0.04 probability that if you live in the suburbs, you'll move to the city in the next time step. Okay. All right, so the question is, given our initial condition x naught and P, notice that P is a stochastic matrix, what is the distribution of people after one time step, which we'll say is 1 year. So we'll do this the long way, and then we'll see how to do this kind of using our matrix computations. All right, so the long way to do this, look at, if we wanted to figure out the number of people in the city, say after one time step, well, how do we get city dwellers? These would be the number of people who stayed. So these are the people who stay in the city plus the number of people who migrate from the suburbs. And so we can compute these two quantities given the information that we have. So first of all, people who stay in the city. We have 50 million people in the city in this time step, and there's a 0.96 chance that they're going to stay living in the city. And we're going to add that to the people who were in the suburbs. There were 50 million of those people, and a 0.01 chance that the suburb dwellers will then move to the city. All right? Notice in this, equals some number, which we'll compute in a minute. Let's head over to MATLAB to do that. So we've got our 0.96 times 50 million people, and then we had a 0.01 times 50 million people, and that turned out to be about 48,500,000. All right, so let's write that down. Let's see, that's 48.5 million people. All right, and then we can also compute the number of people that live in the suburbs after one time step. So if we go back here, how do you get to live in the suburbs? Well, you could either be in the suburbs and stay there, so number of people in the suburbs after one time step. This consists of the people who stay, I'll say the people who stay in the suburbs, and it consists of the people who migrate from the city. So we have two computations that we need to do again. The first one, people who stay in the suburbs. We had 50 million people that lived in the suburbs, and if you're in the suburbs, there's a 0.99 chance that you'll stay there next year. And then we had 50 million people in the city, and there was a 0.04 probability that if you were in the city, you'd migrate to the suburbs. So back to MATLAB. So we can do a 0.99 times 50 million. And then we have a 0.04 times 50 million. And that turns out to be 51.5. million people. Now notice that these are exactly the calculations that would have been done if we had performed a matrix multiplication. Notice that if we did our transition matrix P times our initial vector x naught, let me make these on the same level here. These are exactly the calculations that we would have had. So we had a 0.96, we had a 0.01, and so forth. And when we multiply the first row times this column, this gives us, make a little bit more space here, this gives us the 0.96 times 50 plus the 0.01 times 50. And for our second row times the column, this was our 0.04 times 50 plus our 0.99 times 50. And those were exactly the same calculations that we performed right up here. Notice that we have that calculation right here and right up here. So the matrix calculation is going to be a lot quicker for us. I'll just write these numbers down for us. And more so than that, what's really exciting here is that when we take this transition matrix P and we raise it to higher and higher powers, we're able to kind of predict forward into the future. So let's kind of write some of this down. So note, we got x1 by multiplying our transition matrix P times x naught. So this was our initial condition, or our current time step. This was our next. And this is our probability matrix. And there's nothing special about the x naught and the x1. If we wanted to continue this forward, this is a recursively defined sequence of vectors. Look at x2 would be p times x1. But we know what x1 is. That's the same as p times x naught. In other words, that's just p squared times vector x naught. And similarly, if we wanted to find the status of the people after 3 time steps, or in the third time step, we would be interested in doing p times x2. But we know what is x2. We just computed that. That's p squared times x naught. And so x3 can be found by computing p cubed times x naught. And in general, the nth step, so if we want the state of the system after n minus 1 steps, assuming we start with the first one there, we would have p to the n times x naught. And so this gives us a way of determining the long-term behavior of the system. So we can determine the long-term behavior of the system by letting n go to infinity and take the limit as n goes to infinity of these computations p to the n x naught. Okay. All right, so let's get a few more definitions and then take a look at this. So just to sum up here, we have a Markov chain. What is a Markov chain? A Markov chain is a type of model where the probability of going from one state to the next, or to another, depends only on the current state. And that's in contrast to a system that maybe has memory in it. You know, these systems, to get the next time step, you only need to know information about the current state of the system. Okay, so we'll say rather than a complete historical description. Okay, so let's go back to MATLAB and see what would happen with our city dwellers and our folks that live in the suburbs. So I'm going to let x naught be a column vector with 50 people. In the first row and 50 people in the second row. And let's make sure that's a 0, not an O. Okay, good. Now, let's let our matrix P, this was our matrix of probabilities, was 0.96, 0.01 in the first row. Second row was 0.04 and a 0.99. And that is a stochastic matrix, as we can see those columns sub to 1. Now, if we wanted to find x1, that's just P times x naught. And if we wanted to find x2, that's equal to P squared times x naught. All right, and maybe we want to go out really far in the system. Maybe we want to find, what's happening at time equals 50. Well, we would go P to the 50. So raise that to the 50th power times x naught. And it looks like we're getting more and more people that are living in the suburbs. And if we maybe went out to 100 time steps, P to the 100 times our initial vector. Sure enough, it looks like indeed the suburbs is kind of an absorbing state for the system. Now, when we study eigenvalues and we study eigenvectors, we will learn how to compute kind of the equilibrium conditions more precisely. But for now, I just wanted to introduce stochastic matrices and show you an example of kind of this idea of absorbing states.